Tesla batteries. They're not just the heart of an electric car. They're one of the most advanced energy systems ever built at scale. Compact, powerful, and smart, these batteries are designed to store massive amounts of energy, deliver it with lightning speed, and last for hundreds of thousands of miles. But behind every battery is a stunningly complex process, one that starts with raw metal dust and ends with robotic precision. This is how Tesla batteries are really made, from start to finish. It all begins not in a factory, but in a mine. Tesla batteries rely on a group of essential minerals: lithium, nickel, cobalt, manganese, and graphite. These materials don't come from a single place. Lithium might be extracted from salt flats in South America. Nickel could come from Indonesia or Canada. Cobalt is often sourced from the Democratic Republic of Congo, while graphite is refined in China or the US. Once extracted, these minerals are sent to refinement facilities, often run by Tesla partners, where they're purified, chemically altered, and prepared for battery-grade use. Lithium, for example, is transformed into lithium hydroxide or lithium carbonate. Nickel is purified into a fine powder. Every element is tested and retested. Even the tiniest impurity can compromise battery life. These refined materials are then delivered to Tesla's gigafactories, colossal, fully integrated plants where batteries are built from scratch. Inside, we enter the first major phase: electrode manufacturing. The process begins with what's called a slurry, a thick, wet paste made by mixing the active material powders, like lithium, nickel, cobalt, with binding agents and solvents. This slurry is applied to long, thin metal foils, copper for the anode, and aluminum for the cathode. These coated foils are passed through massive machines that spread the slurry in a perfectly even layer, down to the micron. Next, the coated foil is baked in giant drying ovens that can reach over 150 degrees Celsius. This removes all moisture and prepares the material for the next step, calendering, where the dried electrode sheets are compressed by high-pressure rollers to achieve perfect thickness and density. Once dry and compressed, the sheets are cut into strips, cleaned with high-powered lasers, and carefully wound or stacked into what's called a battery cell. Tesla has used several cell formats: the cylindrical 18650, the newer 2170, and the ultra-modern 4680 cell, a much larger design built for higher efficiency and fewer parts. Each cell is a tiny battery on its own, but the way it's assembled is a marvel of engineering. Inside the cell, the anode and cathode sheets are separated by a porous polymer film called a separator. These layers are stacked or wound in a jelly roll configuration, tight, uniform spirals that fit inside metal canisters. Once assembled, the cells are filled with electrolyte, a liquid or gel-like substance that allows ions to move between the anode and cathode. This filling process is done inside clean rooms with extreme precision. Even a single air bubble or dust particle could ruin the chemistry. Once filled, the cell is sealed with a welded cap and then tested. Voltage, resistance, insulation, all measured and logged. Bad cells are rejected. Good cells move on. The next step, cell aging. Even though they're finished, cells are left to sit, often for days, to allow the electrolyte to settle and fully integrate with the internal structure. It's like curing concrete. Rushing this step can reduce battery life. Once aged, the cells are grouped into modules, rectangular units that house dozens or hundreds of individual cells. These cells are placed in parallel and series configurations, depending on voltage and energy requirements. They're bonded with adhesives or welded with lasers to create stable electrical connections. But Tesla doesn't just stop at modules. Modules are combined into battery packs, which include not just the cells, but also the cooling system, structural frame, battery management system, or BMS, wiring harnesses, and protective casing. Tesla's packs are known for their liquid cooling. using a maze of channels or tubes to circulate coolant and regulate the temperature of every cell. Why does this matter? Because battery performance and lifespan are directly tied to temperature. Too hot, and you get degradation. Too cold, and performance drops. Tesla's system keeps the cells in a tight thermal window, even during supercharging or extreme driving. The battery management system is like the brain of the pack. It monitors every cell's voltage, temperature, and state of charge. It balances energy between cells, manages charging rates, and communicates with the car's onboard computer. If anything goes wrong, even at the smallest level, the BMS knows, and it responds. Now, you might think this is the end of the line, but Tesla does something different. With the introduction of the 4,680 cells, Tesla began rethinking the entire pack structure. They created what's called a structural battery pack, one where the pack itself becomes part of the car's chassis. Instead of mounting the pack to a frame, the pack is the frame. The battery case supports the car's body and handles crash forces. This reduces weight, increases stiffness, and eliminates parts. It's like merging the battery and the car into one unified system. After final assembly, every battery pack undergoes extensive testing. Thermal scans, electrical load simulations, vibration tables that shake the pack as if it were in a crash, waterproofing tests. Tesla simulates worst-case scenarios to ensure that the pack holds up under real-world conditions. If it passes, the pack is cleared for vehicle integration. In Tesla's vehicle assembly line, the entire pack is lowered into place by robots and bolted directly to the car's underbody. High-voltage connectors are attached. Cooling lines are sealed. Sensors are plugged in. Once installed, the car receives its first boot up. Software is flashed. The battery is linked to Tesla's ecosystem, allowing for real-time diagnostics, over-the-air updates, and performance optimization. But even here, the process isn't finished. Tesla tracks every battery throughout its life cycle. From production to delivery to daily driving, the car's onboard systems send back usage data. This allows Tesla to continuously refine their manufacturing and catch issues before they become problems. And when a battery reaches the end of its life, it's not wasted. Tesla has launched in-house battery recycling programs. Old packs are disassembled. Materials like lithium, nickel, and cobalt are recovered, refined, and used to make new batteries, closing the loop, reducing dependence on mining, and lowering environmental impact. So let's recap. A Tesla battery starts with rock. That rock is refined into metals. Those metals are made into powders, turned into slurries, coated on foil, dried, cut, rolled, stacked, filled, sealed, tested, aged, grouped, cooled, managed, protected, integrated, installed, and only then is it called a Tesla battery. It powers acceleration, regeneration, navigation, autopilot, and more. It's the silent force beneath the floor, and every part of it is the result of chemistry, software, automation, and design. Simple? Never. Ordinary? Not even close. This is Process Uncovered, and this is how Tesla batteries are really made. If you learned something new today, hit that subscribe button, because we're diving into even more behind-the-scenes systems, everyday tech, and mind-blowing industrial processes. Leave a comment with what you want to see next, and we'll take you inside the machines that build the modern world. Thanks for watching.